So in previous videos, we have introduced these concepts of energy, frequency, wavelength when talking about light. So if you were to take a sample of white light, like the light that's in this room with me right now, or the light that is coming out of the light bulb where you are right now, if you were to take that white light and filter it through a prism, and this a prism, another piece of glass, it essentially will filter light into the visible spectrum, and it does that because white light contains light that has varying wavelengths and frequencies. And putting it through something that can distinguish between those wavelengths, like a prism, exposing the white light to that will separate it into its different component parts with different wavelengths. So that's why white light is actually a mixture of all the visible colors in the spectrum, that Roy G. Biv that you probably learned in a physical sciences class. So we say that white light gives us a continuous spectrum. We see the entire visible region of colors for white light. We see something very different once we change our sample from white light to a sample of atoms in a gaseous state, in this case hydrogen. If I was to take a lamp of hydrogen gas, excite those hydrogen gas molecules, and focus them through a slit, or separate those components through some kind of detector and the prism, I would see not a continuous spectrum of Roy G. Biv, but I would see that my hydrogen gaseous sample was separated into distinct wavelengths. And if I was to take a picture of those distinct wavelengths using some sort of detector or some sort of film, those distinct wavelengths would be in the form of lines, which you see here. So it turns out that all elements have what's called an emission spectrum. An emission spectrum is the light that is emitted from a particular sample that is excited with a particular energy, and that emission then separated into those wavelengths. So the emission spectrum for an excited atom is different than what you see for white light. You see distinct lines corresponding to distinct wavelengths of energy. And the emission spectrum for an atom is fairly unique. If you were to look at other emission spectrums for other atoms, you would see different patterns. We've got mercury and neon here of two other emission spectrums. Regardless if you have hydrogen or mercury or neon, regardless, you're only going to see line spectrums because you have discrete specific wavelengths observed. And you may think, well, okay, that's great. Why am I harping so much on this? Well, this fact that atoms have discrete wavelengths of energy once those atoms are excited, that led to the first model we are going to talk about that deals with the electronic structure of atoms, and that's called the Bohr model of the atom, named after Niels Bohr, obviously. It was his observation of specifically hydrogen's emission spectrum, along with work done from the photoelectric effect and Planck's work. He used that to propose his model of the atom that said that electrons in an atom can only have certain energy levels. And those energy levels that the electrons have when in an atom correspond to specific energies that have specific wavelengths of light. That would match with the emission spectrums that we see with particular atoms. So since those energy levels are distinct, there's only certain values they can have, we say that the energy in in atoms is quantized. Quantized is just a fancy word to say that there is a specific value that that energy can have. And we're going to talk about how to calculate that specifically for the Bohr model of the atom. We're going to introduce it here and then we'll do an example in the next video. So in Bohr's model of the atom, which is shown by this cartoon here, we're going to think about just hydrogen, If you remember, hydrogen on the periodic table has one electron, it's the simplest atom. So I have a model here where at the center of the atom, think about that as being like the protons and neutrons. I have certain distinct areas where an electron can reside. In the Bohr model, those areas are called orbits. Orbits are designated by this n value of whole numbers. The further away you get from the center of the atom, the higher the orbit number gets. And now let's talk about what happens when an electron, specifically in a hydrogen atom, goes between one orbit and another. So let's look at the first one. Or let's look at what happens when you heat up an atom. If I take an electron, or if I take an atom and heat it up, that electron is going to get excited because you're adding energy to it. When doing that, that electron is going to absorb energy and get promoted to a higher energy level. Conversely, if that electron falls back to an energy level or an orbit that is of lower energy, meaning closer to the nucleus, then that energy will be emitted. So that's what's kind of shown here. You see energy being absorbed when an electron goes from an orbit that is closer to the nucleus to farther away. That is energy absorption. If that electron, which it will, fall back down to a lower ground energy state, then energy will be released. And that energy that released has wavelength associated with it, so there's going to be some particular frequency and wavelength associated with the light that is being missed. So how can we calculate, with regards to the Bohr model, the energy that is involved with this excitation and relaxation of energy? Well, we're still going to use this equation that relates Planck's constant, the speed of light, and wavelength, and doing a little bit of derivation that you talk about in other classes. We can relate that to the orbit of an electron that is at the ground state and a higher state. And that equation that I'm clicking through here, that equation that is derived is this equation right here that says that the change in energy of an electron is equal to this constant, which is a derivation of Planck's constant and speed of light and some other constants. But it's multiplied by the reciprocal difference of the final energy level, the final n, squared, minus the initial energy level. So using Planck's constants and doing some other experiments that we're not going to talk about, this equation can be related to Bohr's model, where we can calculate the energy that is involved in either the excitation or relaxation of an electron in the Bohr model of the atom. So you may note that, oh, there's a negative sign associated with it, with this equation. What does that negative sign mean? That negative sign speaks to if energy is absorbed or released. If your electron is going to go closer to the nucleus, it's going to a more ground state, then the energy is going to be released, and so your energy will be negative. Conversely, if you are moving away from the nucleus, that's going to take energy, and so your change in energy is going to be positive. You're going to be absorbing energy. So in the next, I know that this video is a bit long, in the next video we'll review a few of those concepts and do a practice equation using this equation to calculate the change in energy involved with an electron in the Bohr model of the atom.